keep in mind that you can calculate a G for a given state of your system, or are you being asked for the difference between two totally different points in time, before and after a reaction, whatever it might be. And then the last thing that I did, like I said, that's on this note sheet that I want to maybe point out. So what is the definition of equilibrium? The verbal definition, how would you articulate this? General description of equilibrium. Yep.
Things are at a steady state on a macro level over time.
On the macro scale, things are not changing with time. Things like temp are constant, pressure is constant, volume isn't changing. Free energy isn't changing with time, right? G is constant with time once I've reached equilibrium. Okay. So our description of equilibrium is sufficient time has passed for things to stay constant at a macro scale. Things are still moving around and bumping into each other at sort of a micro scale. So the other things we said are that dG will be equal to 0 and that free energy will try to be minimized. So if you draw a little, this is sort of your reaction coordinate here, and you have free energy here. It's going to be something like this. Okay? G is the minimum, and the slope of the minimum, dG, is equal to 0. Is delta G equal to 0 at equilibrium? The answer is not necessarily. Right? Like, I'm gonna make this an exclamation point. Not necessarily. We talked about the forward reaction for, say, ATP hydrolysis. When we hydrolyze ATP and we go forward, delta G was negative 30 kilojoules. That's not 0, okay? Delta G of a reaction being less than 0 is the spontaneous direction for, say, a forward reaction. And delta G has the same magnitude and the opposite sign for the reverse direction. And so your delta G total or net is equal to the free energy change for your forward reaction plus the free energy change for your reverse reaction, where these two things, delta G forward, is equal to negative delta G reverse. This is equal to 0 at equilibrium, in the sense that the forward reaction and the reverse reaction are happening simultaneously, okay? So we draw this maybe sort of something like, this would be then, the forward and reverse reaction are both happening at equilibrium, and the net change in what's going on from the macro scale, the concentrations of things aren't changing overall, because however much is going forward and whatever is being synthesized, that is being turned back into reactants the other way, and some net equilibrium has been reached. But if you're only being asked for one sort of half of this total, that isn't going to be 0. Don't expect it to be. So just something I want to keep in mind, because sometimes people try to set things equal to 0 when we're only looking at one half of a reaction, and it shouldn't be. Just because we've reached equilibrium, delta G does not necessarily have to be 0. So if we're at a system, if a system is not at equilibrium, it's going to spontaneously change in order to reach equilibrium and try to minimize free energy, right? So if the system is not at equilibrium, it will spontaneously change in order to reach equilibrium. Where it can minimize G, its free energy. So one of the things I just want to set up right here first, just sort of draw your attention to, is that we have an equation for free energy change based on chemical potential. dG is equal to the difference in chemical potential times the movement of the ions going in. I can also set this equal to dH minus T ds. This is a completely valid relationship. They're both calculating free energy, and so if you are asked, if you have a value for free energy and you're also given enthalpies and temp and entropy, and you're asked for, and you have number of moles moving, and you're asked for, I don't know, a chemical potential difference, maybe you don't have this half. You have all of this information. You could be asked for any one of those terms that's missing, right? And even though these have never been set equal to each other before on your equation sheets, they're both set to free energy, right? And so the free energy change will be the same. Just want to kind of, there are two definitions of dG, so it's a valid relationship to set them equal to one another. So what we're trying to build to here today are relating chemical potential to concentration. And then we also want to, who's heard of the equilibrium constant? And you've used it and you've seen it, okay, right? Who's seen a relationship for equilibrium constant and free energy change? Maybe? Standard state free energy change is equal to negative RT, the natural log of KEQ. Has anyone seen this equation before? Right? If you haven't, it's cool. We're going to get to it. We're going to use it a whole bunch today. This is what we're building to. We're building to proving this relationship, and we're going to go all the way back and start with chemical potential related to concentrations, and then we're going to prove that it sets this up.